All right, good time of day, everyone, and welcome to this new MLIR open meeting. Today, I'm going to present about a new concept, MLIR actions. More precisely, it's an extension of an existing concept that was developed a few years ago, namely debug actions. I don't have much slides today, 10, I think, at most 9. So it's mostly going to be a demo, some interactive, tooling and showcasing of this framework. And please interrupt me anytime. I hope we're going to keep it interactive and discuss about possible use cases and whatever comes up. So actions. But first some credit, because I'm showing the work, but I didn't do this all by myself. Lots of people have been involved. Actually, it's been almost a year that we started playing with this concept. Cha-Hong has been very involved in working on this in the spring. Jacques and Jeff have been providing a lot of feedback. And Thomas in the fall was co-host of an intern, namely Axel, who has been working 3 months to make a prototype of this. And so what I'm showing here is my, me taking it to hopefully what is almost production ready to be integrated in MLIR. So actions. Action is a way to encapsulate any IR transformation. That's the simplest way to describe it. It provides a mechanism ultimately to instrument the compiler in a decoupled way. So what can we do with it? And today I'm going to show some example. We can trace the compiler, just like we have pass instrumentations, but at a finer grain. With this, we can implement, for example, compiler fuel or bisection techniques to find bugs. So if you're not familiar with compiler fuel, the concept is that every transformation that the compiler will do will, consume 1 unit of fuel. And so the compiler starts with a quantity of fuel and will eat it up as it goes until it stops. And so basically, we're going to tell the compiler, stop optimizing, continue to lower and generate code, but stop optimizing the code further. And we vary the fuel that we give to the compiler, and we see if a bug that we're debugging, that's when most of the time we're going to use it, is still showing up. And so that's a very useful bisection tool to find issues. If you have a miscompile in the compiler, you can narrow it down to the exact tiling of the exact loop or the exact fusion, or, at the finer grain than even a pass, that occurs. So it's going to be on this particular op, this particular transformation is causing a miscompile down the road in the compiler. And today I'm also going to show some interactive debugging of the compiler, and you'll see what I mean by that. So action versus pass. I wanted just to come back on this a little bit because passes are well known. It's a well-defined contract. The main contract of a pass is that it takes valid IR as input. It's verified most of the time, and it produces a valid IR as an output. And a pass is really useful to define some sort of a phase of compilation. And it's intended to be composable. You can reorder optimization passes, you can reschedule them multiple times. So it's really a convenient basic block to build a compiler. And so around this, a lot of infrastructure has been built, in particular a pass manager and instrumentation for this pass manager. So in MLIR, you have access to all those kind of flags. Print IR after all, it's going to print after each pass. We can print only if the IR is changed, right? So we're going to hash the IR before the pass, hash the IR after the pass, and we print only if something changed. If you have a big module and the pass is running only on a single function, we're only going to print the IR for the function that the pass is touching. You can ask to print the IR only when the verifier fails, or only after a given pass. You give the pass name on the command line, and it's going to print the IR just before or after the given pass. We can time. We can actually produce timing and measurement, statistical measurement for pass executions. And this is all built also with the concept of pass instrumentation, which is a C++ class you can override or derive from in your own compiler, and you can set it up on the pass manager, and you can also have your own code invoked before and after every pass. So none of the infrastructure is really hard-coded in the pass manager. It's all built on top of something that's extensible and that more tooling can be built on. Now, my main take on this is this is great, But why are we so anchored to pass? In particular, the pipeline, the pass manager, this all makes sense. But the instrumentation, there is no reason to be so coupled to the pass granularity. And so while pass instrumentation is a great tool, I think we can do, also at a finer grain, provide some support. And so that's really where action are coming up, trying to make this orthogonal and build the equivalent of a pass instrumentation, but for any level of the IR. So far, so good. I don't see any question on the chat. If no one wants to interrupt me, I'm just gonna continue that. All right, let's stop the slides here and let's get into demo mode. Here is my editor. I have lots of things open, but mostly, we're gonna walk in the terminal. Might be a bit small. Let's see if we can get this a bit bigger. Okay, that should be probably large enough. I have some commands, so just because otherwise I won't remember what I want to show. Let's start with pass execution, right? So here I have an example. This is a test for the sparse compiler, right? So we have some IR here. We have a module with like a matmul, another function with a matmul, another function with a matmul, and here the main driver that is just able to initialize and execute the actual matmul and check the results. So what can we do is that if I print it on the standard output, I get LLVM as an output. So this is really the LLVM dialect produced by the sparse compiler, and it's a not trivial file, I think. Yeah, almost 5,000 lines of IR. So what we have is an option called MLIR timing. Let's cut on the line, but that's the option, -- MLIR timing. If you add this to MLIR opt, this is what we get. Okay. Show the terminal, execution time report, total execution time, and then the full pass pipeline with like the time spent in like absolutes and percentage of the user time and the wall time. We present both because the pass pipeline is multi-threaded. And so often you may see, that there is a difference between those, right? Because we spend more time in thread, and so the wall time is shorter than the user time. And yeah, that's what we get as the kind of information I was mentioning before, right? We can also try to do, if you haven't played with it, print IR before all. So I expect this is going to be a lot of output. Yeah, I'm going to interrupt it. But I search in my terminal, print. Oh, it's dump. Here we have some markers, and I can have the IR dump before the pass named, Linux generalized name dump. And here is the function, this one function that the pass is about to be executed on, right? And I get all of the IR. Yeah, what? Just gonna go back there. So this is the pass name, and so I think print before. We can probably do that. Yes. So I can also execute with MLIR print IR before equal and the pass name. And even though it's going to run the entire pipeline, it's only going to print me the IR before this one pass. So it's going to print it before it runs on the module. Actually, it runs on the module directly. So it's going to print likely once only. Yes, the pass run once because it ran at module level. If it was running on functions, we would see multiple runs of the pass and the print of each function individually. All right. So that's the pass instrumentation. Can show also the code, because I mentioned that you can. So this is a class. It's virtual and it has those callback. So if you derive this class and you register it on a pass pipeline, and the pass manager, you will be invoked, and you have this run before pipeline and run after pipeline. run before pass, run after pass, and those callbacks can be overridden by you to instrument the pass manager. All right, so far so good. I don't know if it's like trivial to anyone or there's some things you learn along the way, hopefully. So I'm going to go back to next. Yeah, so let's see some more logging now. Let's see what we can do with actions. So actually, I threaded through action inside Flang, the Fortran compiler that is in LLVM. And so here I have a very simple, example. If I run Flang on this one example, it takes a while. Okay, so that's a file with like 4 functions doing matrix multiplications. And so I added those options. You can re-execute the compiler by adding -x Flang. That's to bypass the Flang driver. The more interesting option is this one, log MLIR action 2, and then the file name here, Flang actions. And so that's what we're going to do. And we can see what we get out of it. We're going to take 10 seconds, maybe 15. All right, this is the file we get as an output. It's pretty big, lots of things that were going on. So what we see on every line is the thread number. Again, we're multi-threaded. The beginning of an action, we just know that breakpoint was hit. And this is a pattern application action. So for every single pattern matching and rewrites that the compiler will execute, we get a log. And we get a log that tells us the name of the pattern. Actually, the output is, bit threaded, so it's not log. There's no log. But we also get the IR, the actual op the pattern is matching here, and we get the location in the file pointing to the source line, right? And so that's all the tracing of the entire compiler. So we have this, but we also have passes. So for example, here we start a new pass, pass execution action, running the pass simplify region-lite on the operation, this function name here, which is defined at this location. Okay, so these are the location for the arguments. And so we don't print the full body of the function. That would be too much. We want the one line printing. So we skip the regions. We just know that, that there was a region and the location where the function was initially defined. Okay, so now that's a lot. Something that might be useful though is sometimes you may end up looking at some IR that you printed late in the pipeline. And you may wonder, how did we get there? Like, where the IR is coming from, you have the location, but you would want to know what transformation in the compiler you ended up with, the actual instruction you get. Maybe you got a vector instruction and you wonder how you got a vector instruction. When you look at the location in the source line, it may not make sense. So how do you go from a long pipeline, from the end of a pipeline to back to the source and tracing every step along the way? Well, that's another thing where action can help. So we also have a new flag that I added to Flang, the Fortran compiler, log MLIR action filter. And then we can give a location, which is a file name, plus a line, and optionally a column even. But here I just want every action that touches DIR at this particular source line, right? So let's see, we can re-execute it. Should start populating the file. All right. And so here we go. We have not that much, 100 actions. So now it becomes something we can read, right? It's manageable. So we can look for threads, run this canonicalized contract add. So there was this op in DIR that correspond to the actual source line we want. We can also check the DIR, line 184, I think. here. So it's the implementation of a matrix multiplication, right? So lots of math, multiplication, addition. So we can expect some FMA maybe, or vectorization, I don't know. But it's just interesting that we can trace this and find every places where a pattern matched IR that touches this line. So maybe you started from GDB, you had a runtime failure, and GDB tells you it comes from this source line, and you want to know maybe where, how it was transformed, how you got from the source file to this location in the binary. So the idea is to make it traceable this way. Any questions so far? Comments, discussions? All right, so that was the logging I added. It works on Flong, it works on MLIR-opt. It's very easy to add to the framework or to any MLIR-based tool. But we can look a bit more into some more tracing. So what I did was, actually, I think it's enabled by default. I didn't have the flag, I hard-coded it. So even when we run just Flong like this, we should get a profile file generated. Let's see, I have it open already. So I loaded the trace. So this is the execution. Trust me, I already loaded it ahead of time so that, I reduced the failing demo effect. This is an online web interface where we can load like Chrome traces. And so this is the run we're just looking at. We were looking at a textual log. Now we can see a more visual log. So for example, here we see at the top, like this one thread is executed this first pass. When I click on it, we have a pass execution action, and we have details, we have context. So we know that for this time, it was running actually the canonicalizer on the module operation. So it's running canonicalization directly at the module level. Then we have here the inliner, and the inliner internally will run the canonicalizer. So those are 4 canonicalizer run. And, well, I come back to that later. We can zoom in and we can see there are other passes smaller here. Simplify, maybe it's a bit small. I don't know if you can read online. Just gonna zoom in. This is what we see when we click on a pass, right? You see the starting time, the duration. This pass ran for 2 milliseconds. Which thread it ran in, and then the detail here. It was a pass execution running simplify region light on the operation, and here we have the operation printed with its. We again skip the region, but we print the location, which can be again convenient. So going back up a bit, just a bit out, because we won't see anything. All right, so here we have more passes. The UI doesn't like it if I zoom too much. Yep, if I zoom, I cannot click anymore, apparently. Okay, so this is another run of the canonicalizer, and now you may wonder what are the small red dots, and so those are patterns. So here we go. If we zoom enough, we see the pattern application in the canonicalizer, and we see that this one, for example, was the mul of neg f on matching this arith.mulf up, at this location. So we can go back to the source code and know exactly what was happening at a given time. And we see the entire pass manager. So something I noticed, doing this experiment a couple of days ago, is that it's not much threaded actually. If you look at the execution, there are a few threads here horizontally, but overall, the other threads, I don't know what they're doing. They just execute some passes. Like there's only one pass apparently that is sometimes threaded. Most of the time, it's sequential. So why is that? I actually went back to the code, and I noticed that the Flong pass manager was just flat. So here we go. Let's see the patch. I need to send this to Flong. I haven't done it yet. Oh, see, it's not the right flag. This is the right one. Here we go. So basically, the Flunk pass manager was set up with just add pass. So CSE was added at the module level instead of being added on every function. Same for canonicalization, same for simplify region. They were all added on the module level instead of being added at the function level. And so this doesn't change much, except that it gives MLIR and the pass manager the ability to thread and run independently on every function. So this is the second trace, and this is what it looks like after we parallelize it. You cannot have them side by side, and you can zoom this one out. So that was the one before, right? One thread here executing everything, and those threads doing nothing. And this is what we can get after we run. And so you see that this first phase before the inliner is fully parallel, and the second phase now is also fully parallel. They also look much shorter. And so we can zoom on the inliner, by the way, because there's something a bit, unfortunate here, which is the inliner is gonna look at every function, and before deciding if it wants to inline them, it will run. It's what it's called its simplification pipeline that you can customize if you instantiate yourself the inliner. By default, if you don't provide any option, it's going to run the canonicalizer. And so it runs canonicalizer on the first function. We can see probably need to zoom a little bit. We can see it here. This is canonicalizer on the first function. Yeah, of course, I have to zoom out just to click on the second one. Here is the _2 is the second function. And you'll have to trust me that this is function 3 and this is function 4. It's probably too small to read here for you. And so what I found interesting is that we have we lose parallelism here. So there's no call graph. First, there was no call graph in this this module. So I think the pass manager should be able just to ignore those functions right now, maybe. But also because they are not called and they are not part of any call graph, those could be executed in parallel. So we should probably go back to the inliner and add some, threading in between those passes. And then we have, again, this parallel pipeline here before getting into the virtual LLVM lowering. And here, this is the lowering of the Fortran IR to LLVM IR. So it's a direct conversion framework. We can zoom in and we can see all the patterns, but there are conversion patterns now. Here, for example, it's probably, again, a bit small for you, but what we can see on what I clicked, we have an apply pattern action. It's the pattern load up conversion on this particular fear.load defined at this location. So we know where it's coming from and which pattern is currently running. Now, it's pretty unfortunate also that this is running at the module level because it's a module pass. And the reason it's running at the module level is because it has to operate on every function and change its signature. So it has to run on the module. But the thing is that we could have this pass use internal threading by first converting all the functions, their signature, and then for the body of the functions, run in parallel. And so actually, this is what I did. So here's the next, it's not completely working yet, but conceptually, that's what it is. And so we get the same pass, except that now you see the patterns, actually, they are not anchored to those paths. Those threads are not running a separate pass. It's the one pass that was scheduled here, but it can reuse the same thread in the thread pool to schedule the direct conversion framework, basically. And so now we have, if I look at the location, this is line 204, and this is line 80. So that probably corresponds to different functions, which is exactly what we expect. There are 4 functions in the file I'm compiling. And so now this one pass can use 4 threads. Main thread is idle, is asking Jeff. Yes, that's because when you start doing a parallel loop in LLVM with the LLVM, so the thread is idle, it's available to run, but there are only 4 functions. I think that, and I have 12 cores, so I have like more than enough threads. If I had 13 function in this file, or 12 function in the input file, I would expect all the threads to be busy, including the one that dispatch, because implementation in LLVM is so that when you run a parallel loop, I can show you the code. Here, there's one bug there's a bug I have to fix. But fundamentally, the change I made for parallelizing this pass is not big, right? This is the Flank cogen here. It used to do an apply full conversion, and instead I turned it into parallel for each conversion. And actually, I think this is not complete. It's probably in another patch. I had to extract the function conversion before. So this was doing function plus content of functions, and I moved the first conversion for only the functions themselves, the signature, and then the body in a separate loop. And this MLIR failable parallel for each loop. Failable means that the lambda can return a failure, but there is another parallel for each that doesn't return a failure. So if you just want to do parallel for each and you don't want to catch any error, for example, you have to give the context as first arguments. And the way it works, it's going to use the thread pool in the context to schedule the work. And it's going to loop over all the ops in the module and schedule the lambda on those ops in parallel. And the main thread is not going to be idle, but what's going to happen is that the main thread is going to first dispatch all the work, and then it's going to participate in the pool to help. So the thread that is submitting the loop here, after it's done sending the lambda to the other thread, is gonna listen in the queue, and if there are still tasks to execute, it's gonna also pick it up. So it's not like we're wasting a thread for scheduling. And so yeah, you see that part, like making use of threads in MLIR is not very difficult. You have to be careful that you're not introducing races, etc. Of course, but here I'm parallelizing on a module, and I'm executing only on every top level operation. So there is it's going to be just fine. I think what I'm missing, and the reason why I still have a race, because there is some mutable state in the target object here, and so I need to adjust that. But for the demo today, it was enough. I just wanted to show that we can use this tool to get more parallelism. Jeff is saying on the chat that the thread pool has one worker thread per core by default. That's the heuristic that LLVM is running. It's going to start with this. It can be customized. And so there are n+1 threads in the trace. That's a good question. So that would be that this is running the main thread plus the n+1. Yeah, I guess so. I haven't counted, actually. I don't know why I have so many threads down there. Oh, and actually the thread pool also starts thread lazily. And so those are the thread from the thread pool, the LLVM thread pool, and this is the main thread that started, I think. And so the LLVM thread pool didn't start more thread because there was never pointed to that. Okay, that's interesting. Jeff says that in other traces, other tooling that people provide in MLIR, we sometimes see the main thread idle when there are more than enough functions to distribute. Well, we should look into that. Maybe I'm going to add, duplicate the function I'm tracing, 5 more times or 10 more times, and try to see what happens and produce a trace. We'll take this offline, Jeff. I'll follow up on that. Hopefully the main thread can collaborate with the others. Okay. Any questions so far? Any comments? Okay, we'll assume it's good. There's something else I did also that maybe you noticed, maybe you didn't. Going from the previous run here, where this pass was not parallel, I felt that, something I noticed looking at those traces, that we spend a lot of time in canonicalizer, like this canonicalizer and looping over every actions, etc., trying to reapply everything is non-trivial. And the canonicalizer is a fixed point algorithm. It's going to try to iterate as long as it finds something to do, right? And so it has an iteration base. It's going to load a work list, process all of its work list, and if something changed in the IR, it's going to restart, repopulate the entire work list, and reprocess the entire body of the function, basically. So it's going to, if it finds something to do in its first pass, it's going to do a second pass for nothing. And the question is, like, how many iterations are there here that were run? Are we converging quickly? Do we run only like 1 iteration, 2 iteration, 10 iteration? So what I did was, like, I'm going to add an action to trace every iteration. And so on this second trace that I showed later, where I parallelized the last loop, you see this green box, and this green box is now the iterations. So when I click on it, I see that this is the first iteration. This is iteration 1. This is iteration 2. So what I infer from that is that the first iteration found some IR to canonicalize, and the second iteration didn't find anything, and so that's why the canonicalizer stopped. But it's kind of expensive to do nothing, right? Half of the time was spent on, this that ended up not changing the IR. What we may get out of it also is we can find cases where we don't converge quickly. Like, for example, this canonicalizer didn't find anything to do, right? But this is a cleanup after the inliner already canonicalized. And actually the inliner as well, the canonicalizer didn't do anything. So all of those were, because it converged in one iteration, that means nothing. I'm going to take a question from the chat. Can I use the apply pattern actions to, 1, save an MLIR module state before running the pattern? Yes, but you have to be cognizant of threading. I think in general, to be safe in MLIR, if you work with this kind of instrumentation, you are safe to go up when you go to the parent operation until you get an isolated region, right? So in MLIR, we have this concept of isolated up and non-isolated up. So a non-isolated up means that it can use SSA value defined outside. For example, inside a function, I may create an SSA value, and then I will have, let's say, an affine for loop. Inside the body of the affine for loop, I can refer to this SSA value that was defined outside. This is an op that is not isolated. On the other hand, a function, for example, is an isolated operation. Inside a function, you cannot refer to an SSA value that would have been defined outside of the function. Now, why do I mention this? It's because isolated op are ops that we can schedule passes on. The pass manager is restricted to operations that are isolated. So because isolated operation can be running in passes in parallel, you're always safe when you get an operation in a pattern or something to go up to the parent, the closest parent that is isolated, that is an isolated region, because then you're sure that nothing else is running on parallel into this entire scope of IR. You could go up to the module if you know by other means that, for example, we're in a single threaded execution, or that it's a module pass. So you need to have more knowledge than, generic thing. So generic instrumentation should be, safe. And that's the thing. So the second question is like, can we run the pattern? Can we perform a custom analysis to compare the previous save states to the current another state? Well, you can do almost anything. Yes, that's the goal. And I'm gonna get. I see that time is flying. I'm talking a lot, so I should probably move forward. I hope it answered your question, Bamsi. Let me take next. So that was tracing, adding a new action. So you may want to know how this action was added. And actually, it's not that much work to add an action, because that could be a question, like how difficult it is to add a new action and a new dispatch of an action inside MLIR. So here's the patch between the two, profiling. This is the only difference. So I need to include this action header. I create a new class to define my action. So I inherit from the parent, and then there's not much to do actually. You expose a tag. The tag here is what gets printed, right? At least for now. That's what we showed in the timeline in the profiler. But I think we should change what we show in the profiler to include the pass name and those kind of things. And the print method that we can override is going to be what's in the detailed, and so when we click on it, that's why when I click on it, I can see its iteration number, and here's the iteration. And there's nothing more to define an action, a custom action. It can have any private field, etc. And then inside the actual greedy pattern rewrite driver, so this is the tool that contains the work list and apply the patterns. This is the only change. There's not more. And basically, most of the line change is indentation here. So all of this is like indentation. It's not changed. So the only change is here we dispatch, we use the context, we call the dispatch method. We say that we want to dispatch this action, and we provide a lambda, and that's it. Well, that's not it. Then there are a few more arguments. There is what I call context. So when you dispatch an action, you can dispatch IR context. IR context is an array of IR. It can be a region, block, operation that we want to attach to an action. And this context is what's going to be shown also in the detail, right? So here, the context is mostly the region that the pattern is applying to. Actually, I'm not sure what's the region. I would have thought it would have been the oh yeah, because it's not the apply pattern, this one. It's the per iteration. It's like one full iteration of the work list operates on a region. That's why the context is there. And that's the current iteration number. And this is going to be passed to the constructor of the action we just saw, right? So here's the constructor. We get the list of what I call IR unit. It's either a block, an operation, or a region. So it's a heterogeneous list. And the iteration number. That's it. So that's an action, and there's not much code. And so it's very easy to use the context. Anywhere you have an MLIR context, you can dispatch an action, and it gives us instrumentation. All right, so far so good. Oh, I also hacked it into Erie because it's not much code to just add it, and I wanted to see it on more real-world example. So this is compiling the entire mobile net, TF Lite mobile net implementation with Erie. I generated the trace. It's a 1.2 gigabyte file, of course, because we generate a lot of IR, a lot of context. Nothing is optimized, very naive implementation. The overhead is terrible, but this is what it looks like. So if I zoom fully out, we see that there is a long sequential phase, and that's because in an ML model, there is only one main function. And we get some parallelism there. It's because Erie will create, a lot of dispatch and a lot of small functions at the hardware abstraction layer. And this is where we get, a pass manager here that dispatch some more work to other threads. And then we have the trailing of the pipeline, which is like canonicalizer, which is there's fold global pass, those kind of things. So what I found interesting on this example is that if I go back, something you can see quickly skimming through is here suddenly, like you see how big this apply pattern is. I don't know if it shows up well, but we cannot distinguish every single pattern. There are like too many, but this is a big block suddenly displayed. So that means there is one pattern here that takes a lot of time. And if I click on it, what I see here, we can see exactly which pattern it is very quickly, right? It's the TOSA fold constant transpose. So we know that constant folding for transpose on tensors of, 1,000 by 1,000 by 1,200 of float seems expensive, and Erie is spending a lot of time on that. There's a question. I'll take it later. And so we see that all of those actions that I can click on even at this loom level. If you can read, I can read. It's all the same. It's a TOSA fold constant transpose. So we probably should, look at the optimization if there's not something we're missing here. But this seems pretty expensive. Like more than half of the canonicalizer here. Oh no, it's a constant folding pass. TOSA layer-wise constant fold pass. It's a pretty big pass. Half of the time is just the transpose. But that may be also specific to this this example, the mobile net. All right, and so this is a 1.2 gigabytes trace that is pretty easy, doable. You can actually inspect it, and you can also see how here we see what I was describing also earlier. In this case, this is a fusion of tensor ops. We run 1, 2, 3 iteration. We haven't converged 4 iteration. And now it's another run of the greedy. So we run 4 iterations of the greedy pattern rewriter. So that might also be something. So when there are many iterations like that, what it indicates that some patterns are probably not instrumented well enough. And so the work list is not updated and is not tracked closely enough. And so there are some inefficiencies. And yeah, so those are, and then, inefficiencies mean we just reprocess the entire work list when we could have reprocessed only some pieces inside an iteration. All right, I think I'm late on timing, so I need to move on. There was one question. The question was like, does that action require code change to the upstream greedy pattern rewrite driver? can it be injected like pass instrumentation? Yes, for example, to instruments, actually, you have to modify the code you want to instrument, right? There is no magic. If you're in the middle of a pass and you want to instrument the loop tiling, right? Someone has to go say, well, the loop tiling pass should use an action every time it tile a loop so that we can see every loop in isolation. And so that we can also have the compiler fuel, the bisection I was describing earlier. And I don't think there's a way around that. We cannot inject code in the middle of a C++ function. Or at least I don't have a good idea about how to do that. All right. Okay, some interactive mode now. We're gonna stay with Flung, right? It's a Fortran compiler upstream. It's great that we have some end-to-end example entry in the repo. So actually, this is the invocation of Flung. I'm not gonna describe it, but this is exactly the same thing as I was showing at the very beginning, except it's like the more verbose variant. So what can I do? I can load it. That's easy. So I'm in LDB, the debugger, right? I can run. I don't know how long it takes. I think it takes 10 seconds, which is going to skip. And actually, maybe I'm in the middle of MLIR. So I can run the backtrace. Oh, I'm in a release build. No assertion, no symbols, nothing, right? So this is the backtrace. Still pretty much okay. The symbols are demongled correctly. But something we can do, we can import a script. So this is a Python script that install an MLIR command. And so now we have an MLIR command. So MLIR foo doesn't exist, but all of those exist. So what can we do? Oh, we have options. We can do MLIR backtrace, BT. Here's the backtrace of the actions, the nested actions that are currently executed. We are in the inliner, which is running its internal, canonicalizer pass. And so we are inside the first iteration of the canonicalizer, and we are currently executing the pattern mul of negf. Okay, that's a bit more, contextual MLIR information than what we get with the LLDB backtrace, the native backtrace. What we can see also is the context of the current action. So this is a pattern. We know its name already, right, from the backtrace. But when I print the context, I also know actually which op it is currently applying to. And it's running on, I can click there, and Visual Studio Code will be nice enough to take me line 2885. So here, this is a mulf that comes from this line. Okay, great. What if I want to inspect a bit more? Well, actually, we can. Just want to take things in order. We have the concept of a cursor. So there is like state in the MLIR debugger right now where I can do. I can do cursor select from context or cursor S. So MLIR cursor select, and I will select only from this context. So there's only one op here to select from. So I will select op 0, no choice. If I try to select 1, it's gonna complain, but here's the op. Now, so I selected this op. What can I do with it? So the next things that you can see, I can print it. So I can do cursor P. Well, when I print, I also have the lock. By default, it doesn't print it, right? That's the only difference. Not much information. What can I do? I can also look at the op that comes after. So I'm going to do MLIR cursor next. That's the op that comes right after. Next, we have a load. We can try to do cursor previous, right? So we can walk back the IR basically. Oh, and I'm in a debug build, right? So this is I'm back to the mul I was in. So there are no symbols, no dwarf, anything, but I can still, inspect the IR. I can do MLIR cursor parents. Okay, pretty cool, right? We are back to the parent. The parent of this op is the block 0 inside the region 0 of the op function. And here's the function name. It's the third function in this file. Great. Now we have a block, right? What if I print it? Well, when we print it by default, we skip the body here. We don't see the body, so that doesn't help much, but we can force it. If I say -- regions, I think, yes. Now I print the entire block. And so this is the block where, oh, it's a big block. This is the block we're currently running on. I can go to the next block in the region, right? If I do next, before I was iterating on every iteration. Now I'm iterating. Oh, there's no other block. It's a function with a single block, but I can iterate on every block if there are multiple blocks. I can go on the previous block. Well, there's no other block. So I can go up. Now I'm at the region level. If the up at multiple region, same, I can iterate the region. I can, if it's an if else, I can switch between the two regions. I can print the entire region. Well, here it's not going to be useful. It's going to print the same thing as the block, right? There's only one block. And so on. And I can move up, up the stack until the module if I want, and print the entire module. And so you can explore the entire IR. And because we're in a yeah, it's pretty convenient. Like, it's not always safe to do everything. You may crash at some point because you're currently modifying the IR. I just hit Control-C to breakpoint, right, to stop the debugger. Yeah, and I can go down, of course, now by selecting, a child. So, for example, I'm on the module. So I'm going to select, third child is this function. So now I switch to function 4, a sibling, I'm going to select the first child. It's going to be the on-tree region. Now, first child, one block, and I can select the 10th up in the block, for example. And here we go. So we can traverse the entire IR with the cursor. We also have breakpoints, right? Breakpoints is a concept that is, in the pure MLIR tradition, pluggable. You can define your own breakpoint concept. Maybe you work on TensorFlow and you want to breakpoint on node names. You could have a, TF break on break, and then, node name, whatever matmul, right? You can break on anything that you want to invent. You have to implement it, though. You have to plumb a new breakpoint as a C++ breakpoint into the framework, but it's injectable. It's purely decoupled. So what I'm showing here is break on file. It's a built-in breakpoint, let's say, one that comes with MLIR. And it takes a file name plus a line and optionally a column. Well, actually, it's exactly the same implementation as the filtering of the action that I showed at the very beginning. So I had a breakpoint. Okay, great. We have a breakpoint now. I can restart the execution. So note that the state of the breakpoint is in the debugger, not in the instrumented process, right? So I restart the process. When it restarts here, we see that the MLIR debugger is attaching to the process that just started. The breakpoint was set on the process. And here we go. This is the first hit we have. Apply pattern, arid ad hop. And so if I do MLIR context, we should see that we have the location I ask. I ask for line 184, and that's what we get. Now I have an MLIR breakpoint. I haven't applied the action yet, right? The pattern is about to be applied, but we could actually decide to skip it. So I can say skip. And now the pattern was not applied, and we just skipped it and continued the execution. Something doesn't seem right. So I was expecting it to break very quickly. Yep, not what I was expecting. So I probably have a bug somewhere. I can apply the pattern and continue. Yep, again, not what I was expecting. We can step into, we can finish, just the same concept as regular debugger, right? Next step, finish. But skip usually doesn't exist, but here you can skip. And skip is what's going to be used for compiler fuel, actually, or for other kind of tooling. You could say, actually, I suspect I have a problem with this pattern. Let's just do a run where I disable this pattern. You can do that without actually rebuilding your compiler. You don't have to go disable the pattern in C++. You can just like filter it with those kind of APIs. This we have the tooling that now that allows to do that. I think I'm very late on time. I thought I wouldn't. I thought I would be done in like half the time, but it turns out I have a lot to show. We can list the breakpoints, of course. So this is a regular, debugger features. So nothing fancy. And I think I showed the backtrace. You can break on tag if you want to break on every new pass execution or anything. breakpoint tag pass execution action, right? Now, if I run, my first breakpoint is going to be executing the verifier pass on the module, right? And if I continue, I hit another verifier. Here we go. I hear up to a pass adapter, okay. And multiple threads. Here we go. Multiple thread actually hit the breakpoint at the same time. That's what we get. All right, that's it for the debugger. Did I have something more? Yeah, I think I'm gonna stop here with the demo and get back to the slides because we don't have much time left. All right, so that was the demo. There are just examples, some tools I built to showcase the framework. The framework is really intended to be pluggable. The goal is to inspire you to build more of those kind of tooling into your compilers and also upstream to MLIR what can be useful, you know. So we need more actions in MLIR, more dispatch in MLIR and in your projects. The ideas like snapshot the complete IR after every transform touching a specific location. This is the kind of tooling we can build. Collect statistic on timings, right? I may want to know the average timing per, but grouped per pattern, you know. Those kind of things. You can build breakpoint for your own project. I mentioned this. I mentioned this as well. We can implement some selective O0, you know. For example, I can give a range of location in the source code and says, you know, compile my Fortran code, but don't optimize anything between line 100 and 105, right? That seems pretty cool to be able to do that. And we can do that by just skipping every action touching these lines of code. It's not a fully O0 because we're restricted to what is instrumented in the compiler. What is not instrumented is not gonna, you know, be able to honor those requests, but that's pretty interesting. This is the overview of the implementation. We don't have time, so I'm going to skip it. But you have to understand that right now, this execution context is what contains breakpoint on state. It's not meant to be the only way to hook there. Like the MLIR context, this is one implementation of the callback that of the handler that handle the dispatch. So basically transforms, when we instrument them, they dispatch the execution to the MLIR context. The MLIR context just checks if there is a handler, otherwise it directly executes. If there is a handler register, it just dispatches the actions. And so the execution context is the one that I implemented for MLIR. You can register observer directly with it so that we can have multiple observers. That's how action logging is implemented, for example. Or you can also attach a controller. This is how the interactive debugging is implemented, for example. It's what decides what to do for every action. And the execution context, you can inject your own type of breakpoints directly there if you want to. All right. And with this, performance overhead is always a question. I really think this is something that is designed to be enabled in production build, because the feature itself, we don't need compile time flag, because the cost of the dispatch when you don't enable the tracing is a pointer check on the MLIR context. So if to dispatch a pattern, you just have to do if, you know, I have a handler, that seems reasonable to me, but we can discuss that. And so you pay cost when you have a callback, right? Managing breakpoints, managing interactive debugging, that has a lot of state. When you start doing logging and you have to print the IR, you know, printing, building strings, writing to disk is very costly. My very naive implementation shows, you know, 10 to 20x slowdown on ERI, for example. But, you know, it's writing big text file is not optimized at all in any way. It won't replace a real profiler, but it's very complementary. It includes a very different kind of context that you get compared to a regular backtrace. And it's pluggable. You can do a lot of things with it. So what's next? You know, I think we should really build this compiler fuel. So actually debug counters exist in MLIR for 2 years, I think. So we can already do this action, you know, the action concept already exists, but it was never used, right? And it was not with a dispatched. The only thing we could do was ask the context, the MLIR context, should I execute this action? And then the debug counter or the compiler fuel was meant to, decide and say yes or no and iterate. But so we implemented this 2 years ago, and it was too limited, and we never made any use of it. There are 0 users in tree, and I'm not aware of anyone actually deployed it out of tree. But something else I'm looking at is the contract with the dispatch. When you dispatch an action, what you get back. We could, have the Lambda returns an action results, which could be a handle to an updated IR unit. Now when we have a logger, we can say, oh, the IR changed. Here is what it was before. Here is what it is after. Here's the kind of thing we could implement. So we could implement more tooling if we had those kind of metadata returned by the implementation. But, it's a trade-off, because now the implementation needs also to return those. Right now, the Lambda doesn't return anything. I'm also looking into adding multiple tags. For example, right now, when I dispatch a pass execution action, the only tag we get is that this is a pass execution, or this is a pattern execution. We could have an array of tags. The first tag would be, this is a pass execution. The second tag would be the pass name, for example. And the third tag could be textual location, or, we could imagine many things. But if already there was 2 tags, one would be that this is a pass execution. The second one would be the pass name. That is a pattern execution, and here's the pattern name. That means tooling that operates generically on tags would be able to match and decide what to do with those. So to be investigated. And that's it for me today. I'm available to take any question you may have, but we have to be cognizant that we're out of time. So I suspect most of the discussion will continue on discourse. And Scott mentioned that Tracy captures also have a lot of overheads. So Scott is asking how much of this action framework is already merged available. None. Actually, it's in a branch in my GitHub repo. I can post it. Actually, I should send the draft Fabricator revision. I'll do it by the end of the day. I've been so busy, building this demo. It was really put together in the last few days. And so I probably have some little code cleaning to do, but most of the code is ready. I spent the last 3 weeks, making it ready to be merged almost. I suspect it's going to take, I don't know, let's say a month. Well, actually, if you're interested in reviewing code, please ping me. I'll add you on the review. I think it's always better to have more eyes and more help for getting code reviewed. That's what takes time. It's appreciated. But yeah, let's hope, optimistic view, in a month, all of this is in tree. But we'll see. We'll see. It depends if there are things I did that are controversial or not in the code. Any other question, comments, interest? You can unmute yourself if you want to, ask anything. All right. Well, if there is nothing else left, we can leave it there. Feel free to ask anything in the discourse RFC. And we'll take it from there. All right. I don't see any more question. Have a good day, everyone. And see you next time.
Thank you. Bye.